Well, in the next, we will consider the generalization risk of evaluating. We'll consider the risk of evaluating single hypothesis, as we have said. So the conclusion is that for a data set of a decent size, of sufficient size, the error rate we evaluate some hypotheses on the trained data set will not differ too much from if we would be able to evaluate that on the entire data population, which is just a hypothetical thought, because in reality we do not have access to the general data distribution. We will, in this discussion, consider the generalization problem of learning a two-class classification problem. So to remove all the complexities involving dealing with other types of risk or multi-class classification schemes. So now it's simple. We have a positive and negative prediction, and which makes the ideal risk or costs very easy to define. We just need to calculate to count when the hypothesis makes errors on either the data point, data points in the training data set, or in general on the data population, in the data population. So the conclusion is this. The equation looks a bit mouthful. Let us explain that a bit. So basically, it is saying that when you evaluate a hypothesis, the in-training error on the data set in the training data samples, the in-sample error, then you get some evaluation, you get some performance assessment. This assessment, if it differs from the generalization error, this difference exceeding some threshold, and the probability is small. So the intuitive understanding can be like this. So basically, it's saying that when we evaluate a hypothesis on the training samples, so it can make some errors there or there, and it is correct on the other data samples. So then you can have some in-sample error. Let's call that A in of hypothesis H. So please note that the focus here is not to have H to be a super good hypothesis. The focus here is that we do not want this evaluation on H differs the true merit, the true performance accuracy of H too much. Let's call this as a data generation process. This is a true distribution of data. And if we apply H on the data distribution, let me draw a cloud to show this is some kind that is cloudy, that is blurred, that is not directly accessible. We call that the out of sample generalization error of H. They are not necessarily the same, the in-sample error and the out-of-sample error. If they are not the same, there will be some difference between them. And we do not like the difference to be too large. If it is too large, that means the evaluation on the training data samples of H is unreliable. It's of no use for us to evaluate how H is good or bad. So if this difference is exceeding some threshold, we call that a bad thing. This is bad. And the learning theory tells us that the probability of such a bad thing happens is small. So we are talking about the probability of this bad thing. I re-emphasize here, the bad thing is not about H performs bad. The bad thing is about the evaluation of H, whether it be good or bad in the data sample differs from the true performance of H in the true data population. When this two assessment of H differs from each other, exceeding some predetermined threshold, we call this is a bad thing. Our hopeful theory tells us that the probability of this bad thing happens, know that there is no guarantee that such bad thing won't happen ever. The bad thing can happen, but it's unlikely to happen. The probability it happens is small. How small? It is, at most, it is up-bounded by 2 times exponential. Note, here comes the interesting part. How small the chance of bad thing happens is determined by how large is the training data set. And the chance of bad thing happens decreases with the size of the training set exponentially. That is, to the power of this exponential minus 2n times epsilon of the square. So because epsilon is predetermined, this is a threshold. We used it here. So take it as constant for now. Then we can see that the chance that bad thing happens decreases exponentially with the size of the data set, which means if for some size n0, if you have such a chance, see here is 1 and here is 0. If for n0, let me put 0 here. So let's call this n0. This is the number of training samples. Okay. If this is some chance of bad thing happens, is intolerable, and you want to make the chance smaller. So by doubling the training data set, see when you arrive at 2 and 0, you will have the chance decrease by this amount. And how much you have decreased it, because this is decreasing exponentially, what we can see is maybe you decrease by a large amount, maybe it decreases by a small amount, but when it decreases, you have the portion of the decrease. See, if the chance here is 1, the chance here is P0, you have P1 over P0 is something less than 1. Then, if you take more training samples, say you arrive at 3 and 0, then the portion by which you decrease P0 by increased number by N0, from N0 to 2 and 0, It's the same as a portion. You will go from P1 to P2, P2 to P over P1. Those two portions are same. When you increase it by another n0, now you have 3 n0 training samples. Go so on and so forth. So this decrease is this means the decrease is exponential and the decrease is fast. So this is a blessing, and of course, the exponential decrease of the risk of a large difference between the in-sample error and out-of-sample error is moderated by how strict you want to define such a blessing. Obviously, if you are happy with those in-sample error and out-of-sample error differs for something like less than 10%, so you will have here 0.01, which will cancel your effort, make your effort of increasing the number of training samples by times it with a small portion. Of course, if you want this to be 0.0001, then the square of this number will be 10 to the power of -8. Then you will need to increase a lot of training samples to get the same amount for guarantee as if you are more tolerable. But this said, the number of epsilon is fixed, is a constant here. So as long as we have set everything up for the problem, and we then can increase n, and the risk of get large difference between the two kind of errors for a hypothesis will drop exponentially. So this equation is called HOEFFDING'S equation. It belongs to the family of large number theorem of statistics, and its contribution is devoted to HOEFFDING, and that is one of the bedrock of our statistical learning, and that kind of laid the foundation of our argument that by learning empirically, by good chance, we can at least evaluate how well our hypothesis against the reality. So to make things more concrete, think about the example of iris data. Okay, well, this actually happens to simplified iris flower data, but actually this applies to any kind of a problem with two attributes. In this example here, I have used sample length and sample height. I extract two attributes from the iris data, and I try to classify those flowers as two classes. So if you have no idea about what iris flower data is, you can Google that. It's one of the most famous, commonly used data set in machine learning. But for now, our discussion, it's sufficient to understand the data has two real valued input, and I want to classify the samples into two classes. Well, it is simplified flower classification. In the real flower classification problem, it's a 3-class classification problem. Say, for example, This is my hypothesis. My hypothesis is simple. I don't care about one of the input variable or attribute at all, and I will split the data space in this way. For those part, I classify them as one class, and this part classify those samples in another class. But just say, for example, the underlying truth of this problem goes this way. So for this part of the class, this should belong to the purple class, and this belongs to the yellow class. Then the golden standard or the generalization error would be for me to compare my hypothesis with the underlying hypothesis and get the correct area and the incorrect areas. So, and the generalization error of this hypothesis, this particular top-bottom split hypothesis, would go this way. We integrate over all possible points on the data space and calculate accounting for wherever the prediction of H is not the same as the underlying truth, and take this over the entire size, the size of the entire data space. This is the generalization error. But unfortunately, we will not be able to evaluate this error directly. So what we can do is we can examine our hypothesis against the training samples. So the samples are drawn from the underlying data distribution, and when we compare our hypothesis against the training samples, we'll find, okay, our hypothesis makes errors on those samples, and it is correct, those samples. And then we can calculate the portion of those samples and get an in-sample error. This could be different from the out-of-sample error, but this is computable because we can, for each of the training samples, and carefully counting where the hypothesis makes mistakes and take this value over the size of the training sample. So while in the out-of-sample error, the generalization error, we do not, for one thing, we do not have the entire data space. We cannot do this integration. For another thing, we don't know the ground truth for any sample that is outside the training sample. Okay, you get the idea. In all the above calculation, what is important is the ratio between the red area and the green area, or the red area over the entire area. So with this understanding, let us illustrate the situation more intuitively by organizing these areas in this way. And HOEFFDING'S inequality is what that's saying is that because when we are taking the data set, we don't know what kind of hypothesis we will compare. We will use the data set to compare with. So with a hypothesis, it will color the data space into red and green area, and the ratio between these two kind of area is our concern. But the process of drawing data samples is independent of how we had colored the data space. Okay. When we draw the data points, it has no idea what hypothesis will it be used to evaluate, and it is the hypothesis using our illustration here. It is that hypothesis colored the data space. So the color of the data space is independent of the joining of the data samples. Because of this independency, we would like to see if you take the portions of the red or the green data samples you have drawn, which representing the data samples where the hypothesis make errors or being correct. The portion should be approximately the same or similar to the portion of the red and green areas. And the chance of taking a set of samples where the portion of the colored points in this sample differs from the underlying portion of the two colored areas exceeding some threshold will be decreasing with the number of samples, which is as we have repeatedly talked about this this concept here, which becomes more and more intuitive to understand. You can imagine the process of sampling from the data space. If you have only a single sample, n equals 1, obviously you will have this in-sample error and out-sample error. It's likely to be differ with a large amount because with one sample either to be 100% correct and 100% incorrect. With more and more samples, say if they were distributed evenly on the data space, but you try to make a large difference of the portion of different colored points in the samples and the portion of the colors, you have to somehow bias the sampling process against the underlying ratio. The more samples you have, the more difficult for a random process to be biased largely against its underlying ratio. And that is the intuition. So for rigid derivation, please check out the central limit theorem in statistics. So far, we have discussed the statistical guarantee of the risk of evaluating single hypothesis. We will move to the next part and consider the risk of evaluating learned hypothesis from a learning process.